Hello, everyone. In this video, I am going to be going over the common fate mediation model using lavaan. The common fate mediation model is just an extension of your traditional mediation analysis or your analysis of indirect effects, where the relationship between your independent variable and your dependent variable is accounted for by a third intervening variable, which is your mediator. In the common fate model, we're kind of extending that framework just to where your mediator is at the dyad level. So rather than it just being, childhood abuse is linked to depressive symptoms through attachment, and that's at the individual level, we're going to examine mediation or indirect effects at the dyad level, where it's couple level, relationship mindfulness is associated with couple level relationship quality through dyadic coping or couple levels of dyadic coping. All right. And so, just to orient you to what the model looks like, if you're unfamiliar, this would be your common fate mediation model, where you have three common fate latent factors. You have them right here, right here, and right here. And there's going to be your independent variable, you have your dependent variable, and you have your mediating variable. And just as in the traditional common fate model or the baseline common fate model, you have all the factor loadings fixed to one, and then you co-vary all the within person kind of reporter effects. So for mothers and fathers, you're going to correlate all of the father's reports on the observed indicators with each other, and you're likewise going to do the exact same thing with the mothers. And so this is just again a general introduction of a way to visualize the common fate mediation model. And again, a lot of this should look familiar, particularly the structural portion of the model down here, if you have done other forms of mediation analysis. All right, so moving into lavaan and moving into R, we are going to use lavaan, which is the SEM framework within R. And then I have an SPSS file, so I'm going to use Haven, a package to read in that data file. And so you can go ahead and you can run these, right? And so you got no error messages, so everything looks like it entered in correctly. All right, so moving into the actual mediation model portion of this, if you've watched the other videos on the common fate, the baseline common fate model, this is just a very small extension of that. So in the other videos, I'm going to actually comment out the indirect effect or the additional effects. But in the previous video, I ran this exact model. And in here, we're just now adding in that mediating variable, which we're going to say is dyadic coping or dyad levels of dyadic coping. All right. So if you're unfamiliar with the common fate model, I will refer you to the other video that I did on the baseline common fate model. And so first, we are going to estimate the the three latent factors that are the common fate variables. And so we're going to have relationship quality. This is going to be our dependent variable. We have relationship mindfulness, which is going to be our independent variable. And we have dyadic coping, which is going to be our mediating variable. So each one is going to be, each factor loading is going to be constrained to one. And you do that by uh, using one star in lavaan. So this is telling lavaan that this factor loading that loads onto this variable is going to be constrained to one. Right? And you do that for every single one. And so that creates an unweighted kind of dyadic mean of sorts. All right. And so what you're really doing is you're accounting for shared variance between males and females reports of relationship satisfaction, relationship mindfulness, and common dyadic coping. Right. So this is your measurement portion of your common fate model. And then here's the structural portion. And this is where you have your dependent variable regressed on, so the tilde is being regressed on, your mediator and your independent variable. and then you have your mediator being predicted by your independent variable. All right. And so essentially what that part of the model is there's these three gammas right here, or gamma one, gamma two, and then beta three. All right. So that's the structural portion, and the measurement portion is just estimating these three latent factors that I am highlighting here. All right. So moving back over to R, we need to estimate the covariances for the male and female reports. All right, so the male reports are associated with all other male reports because what we're essentially saying here is that there's some common unmeasured cause of an association between male reports of relationship satisfaction and relationship mindfulness. So, for example, it could be that male partners general tendency to be more neurotic, right? So that might be a common cause that is going unmeasured by the dyad level variance that is captured by the common fate latent factor. All right, so we need to account for those unmeasured common causes. So that's what we're doing by implementing these residual covariances. And so we're going to do that for all three. So we should have three coefficients or three residual covariances: relationship quality with relationship mindfulness, relationship quality with that dyadic coping, and relationship mindfulness with dyadic coping. And then we have the exact same thing down here for the females. All right. And so down here we are going to tell M or not M plus, we're going to tell lavaan to create a model fit object, and we're going to specify the model. We're going to tell lavaan what data we are using. We don't necessarily need the mean structure here, but this is standard output that I request. And then I'm going to use robust maximum likelihood to account for non-normality in our dependent variable. We often find that relationship quality is a highly skewed variable, especially in the residuals. And so I want to account for that so we can get more precise test statistics. All right, and then down here, we're requesting lavaan to give us the actual output. We're creating a fit object here, but that doesn't necessarily mean lavaan's going to give it to us. So we have to request the actual output. And the fit.measures will give us our CFI or TLI and things like that. By default, lavaan will only give you your chi-square statistic. We want standardized estimates. So we can talk in standard deviation units because oftentimes that's a little easier to understand rather than the raw metric. And we want to know how much variance is being accounted for by the model. So we can go ahead and we're going to run this model. And generally, this is the first step, just to see if we get any error messages. That's really the primary purpose of me running this model first, because we are actually going to test the indistinguishable model next. So I just want to be sure that we have a good solid base and that we're not running into, again, error messages, because if we run into error messages when testing and going straight to the model that is testing distinguishability, it might be from the distinguishability test itself, or it might be from the poor fit of the baseline model. And so we don't really have a way to determine that. So that's why I always start here. Another reason I start here is I want to look at those factor loadings, those standardized factor loadings in particular, because to use the common fate model, it's recommended that we have factor loadings above 0.70 for all of our variables, which would indicate that approximately 50% of the variance for each dyad member is at the dyad level. Of course, we can have, like when we think about relationships, we can have, you know, my perceptions that are kind of shared with my partner. And I also have my individual perceptions that are unique to me, right? And so we want those shared perceptions to really have a substantial amount of explained variance or shared variance. And so we want that number to be around 49%, which equates to our factor loadings of being 0.70 or above. Right? And so we look at all of our common fate latent variables, and all of them are above 0.70. So we are in really good shape with being able to use the common fate model. If you have factor loadings that are below that 0.70 threshold, there's a couple of things that you can do. You can estimate a latent congruence model, which is estimating the dyadic mean, which we're capturing in this study, that random intercept. That's what this variable is. And you estimate a second latent variable that's actually a difference score or a congruence score. Another thing you could do is you could actually estimate the common fate latent variable model, like we are here, but then you can use phantom variables to in the residual portion to estimate those individual parameters, because what those flow factor loadings are telling you is that there's more and more variance at the individual level, and there's less and less shared variance. So you need to model that individual variation, and there are ways to do that. All right, so I'm not really going to interpret these other outputs because we need to do some other things before we kind of come to our final model. I'm just going to kind of take a glance to see kind of where the parameters are at, and just again just get a general understanding of what the effect sizes are in terms of regression coefficients. And then I want to go down here and I want to look at R squared, to see how much variance our model is accounting for. And again, it's doing a really good job, particularly for couple satisfaction, right? So next, we are going to test distinguishability within the common fate model. And so what you will see here is it's the exact same model as above, but I've added labels in several areas of the model. All right, so you'll see I have added labels on the covariances. So the residual covariance between male relationship quality and male relationship mindfulness is constrained to be equal to the residual covariance between that same parameter among the females. So relationship quality to relationship mindfulness. All right. And I've done the exact same thing for all the residual covariances. So we are kind of forcing those residual covariances to be equal across gender, which is essentially saying that the unexplained common causes of an association between CSI and RMM for males is exactly the same as those for females. Right. So again, if we're testing distinguishability, if men and women are different or not, we have to constrain these parameters to be equal. And as we can see up here, the unstandardized loadings are actually already constrained to be equal, all right, with those ones. And so we're actually going to do the exact same thing with the item intercepts next. All right. So the item intercept for relationship quality is constrained to be equal for men and for women. And so you'll notice you can use any labels here that you want. I use tau because that generally is an indicator in like factor analysis and structural equation modeling of observed variable intercepts. So that just helps me kind of organize, and psi is your covariance matrix. So I use that when I'm constraining those residual covariance. You could also use theta here, but it just helps me kind of keep myself organized and what is actually happening and what's constraining to what, and kind of where that's showing up in the model. All right, so after constraining all of the residual covariances and all of the item intercepts to be equal, we are going to get an additional 6 degrees of freedom. All right, so we are now estimating half as many parameters as we were in that original model in the context of the residual covariances and your item intercepts. And so we should get an additional 6 degrees of freedom, and the baseline common fate mediation model has 3, so we should get 9 degrees of freedom in our model, which means essentially that we are placing 9 restrictions on the model, and we're going to see whether or not that's a reasonable thing to do. So we can go ahead and we can run this model. And if we get a non-significant chi-square difference test, that tells us that that the men and the women in this sample, it's heterosexual couples, are not empirically distinguishable from one another, not empirically different from one another. They might be at a theoretical level, but we need data to back up that theoretical substantiation. All right, so what we can see here is our model fits our data quite well. So we have 9 degrees of freedom, and our chi-square value is quite low at just over 9. We have CFI and TLI. Our values are good. Generally 1.0 is a near perfect fit. And then we have our RMSEA. We want that to be as low as possible. And we can see here that it is really quite low. And we have a somewhat wide confidence interval. I think that's actually a good indicator um, of how well the model the RMSE is actually measuring model data fit, because you want those confidence intervals to be really, really tight. But the wider and wider they get, the more variability that we are entering into. With only 9 degrees of freedom, this is actually a fairly tight confidence interval. The RMSEA is subject to bias in models with small degrees of freedom. So it tends to behave either really, really, really well, and so you get really low values like this, or it tends to have really high values. So this is like 0.10 and above. So I don't really give a whole lot of weight to the RMSEA in these smaller degree of freedom models. Generally, when I'm getting to 15 to 20 to 30, that's when the RMSA becomes more and more important. But here it just it's something I consider, but it's not really the end all be all. I kind of take a gestalt approach when the chi-square statistic is non-significant. CFI and TLI are behaving really well, and my RMSEA is behaving really well. I can say with a lot of confidence that this is a really good fitting model. Um, and you'll see the factor loadings probably changed a little bit, not a whole lot, and nor should they. But again, SCM is a systems of equations um, type of analysis. And so if you change things in one part of the model, like restricting means, restricting covariances, you will see shifts in your factor loadings a little bit. This is going to be particularly true for those residual covariances that we constrain to be equal. But you should not see any drastic changes. Here is a good indicator that you got your syntax correct. You can just double check everything, and variables with the same label here are constrained to be equal. And so here you can just double check. I have uh, relationship mindfulness being constrained to be equal to relationship quality, and that looks good. All right. So we can scroll down, and the most important part of the output is going to be this test right here. And so you can see we added 6 degrees of freedom, right? So those the constraining those covariances and those item intercepts to be equal to one another across gender did not significantly harm the model. Our chi-square only went up by 2.83, but we got 6 degrees of freedom, which resulted in a fairly low p-value, which means that these restrictions did not significantly harm the model data fit. All right, so this tells us we can actually use this more restricted, more parsimonious model in future models, because men and women don't differ on the variables in our equations. And what this will do is it will allow us to better evaluate model data fit. It will also increase statistical power, since we are telling the software to estimate fewer and fewer parameters. All right, so then the final thing that we'll do in this video is estimating the indirect effect from relationship mindfulness to relationship quality via um, uh, dyadic relationship level dyadic coping. Okay. And so you will notice that this is the exact same syntax as above. So I quite literally just copied and pasted it. The only thing that is different is I have now specified syntax for calculating an indirect effect. And so all I am doing here is multiplying the A path, which I have now labeled here. So this is the path. I'll pull up the diagram here. So that's going to be your gamma one. All right. So this is relationship mindfulness. This is dyadic coping, and then this is relationship quality. I am labeling this path right here to be alpha. All right. And so then you'll see I also added a label beta. Again, this is again one of the only changes I made. And that is the path from dyadic coping to relationship quality. So that is this path right here. That is beta 3. All right. So I am literally going to multiply the effect from here, this regression coefficient, this gamma 1, to times the times beta 3, or the beta path as I have labeled it in lavaan. Right. So I'm adding these labels so I can construct the indirect effect down here. All right. So without these effects, it's going to be it's going to not be possible in lavaan to estimate those indirect effects. All right. So what you do to estimate indirect effects when you create any type of effect in lavaan, um, you name your indirect effect, and then you do the colon and the equal sign, and then you add in those labels that we added up here in the structural portion of the model. So I actually need to rename this. This is the structural. Right. And so this is again using kind of good old-fashioned kind of delta method, where you were just again multiplying the past times one another. Um, Typically, one of the criticisms of delta method is that indirect effects are not normally distributed, and so that's again one of the problems with doing this approach. Um, I will actually be limiting the impact of that, because essentially what happens is delta method, it compares uh, the the indirect effect that we're computing here to a normal distribution, and we're kind of matching them up to see how close they fit to one another, and it generally doesn't go very well, because even if these are normally distributed, when you multiply two normally distributed parameters by each other, it leads to a non-normal distribution. And so I'm going to do the best I can to address that using robust maximum likelihood, which is again is going to adjust those standard errors. So for the non-normality that we see, and you will see in this example, if you compare maximum likelihood without robust to robust, it won't really matter because we have such a strong indirect effect. But when your indirect effect is saying p equals 0.03 versus with maximum likelihood, versus where if you implement robust maximum likelihood, your p might be 0.06. That tells a very different story, and it might matter, but it won't matter in this analysis. All right, so we can go ahead and we can run this model. All right. And so again, we should have, again, the same degrees of freedom. We didn't really do anything different to the model. Our model fit should be identical. So if you compare this model to the model above, they should be, again, perfectly identical, perfectly replicatable. All right, all we've done is kind of added a new parameter that's multiplying, again, our alpha path times our beta path, which won't affect model data fit, nor will it affect our standardized estimates or really anything else in the model. But what it will do is it'll give us this parameter down here. This is our indirect effect. Here is our unstandardized indirect effect multiplied by the standard error. We have our z value, and then we have our p-value, and then our standardized indirect effect. All right, so we have a highly significant beta equals 0.383. And then that tells us that we have, again, a highly significant, really strong indirect effect from relationship mindfulness to relationship quality. So what I will do briefly is I will illustrate this with just without robust maximum likelihood, and we'll just take a look at the standard error differences. So up here in the previous model with robust, our standard is 0.112. All right. And so down here, it's 0.107. So you see a small little change, right? You'll see that the parameter estimates didn't change at all. And what happens is maximum likelihood without robust standard errors are most of the time going to give you a type 1 error. So again, in the example before, when I said maximum likelihood, it gives you a p-value of 0.03, but robust gives you a p-value of 0.06. Uh, what robust do is it's going in and correcting the chi-square, which is going to affect how you calculate your standard errors. And so robust maximum likelihood will be the more conservative test and the more appropriate test when you have non-normally distributed residuals. So in this case, it doesn't make a big difference, but in other cases, it could actually go on to you would read a completely or write a completely different discussion section. So hopefully this has been helpful in estimating the common fate mediation model. And again, if you're unfamiliar with the common fate model, I have other videos that go over the baseline common fate model.